We will continue with our boundary layer theory, the order of magnitude analysis. We mentioned that Prandtl used a rough estimate of various terms to decide which term should be kept and which term should be discarded. So how does this work? To give an illustration, let's say that somebody gives you a function of x, just a graph. You don't know anything about the actual numerical values or anything like that. They ask you very quickly, what is the slope of the curve at point A? What is this particular slope, for example? If you are given only one piece of information, let's say the function f at A, and then this is the distance over which it goes from 0 to function at A, then you will say, okay, over a distance of xa, my function has risen fa, therefore I'm going to estimate or guesstimate the slope as fa over xa. So Prandtl had very limited information about viscous flow, therefore he just used these type of arguments to guess what the values should be. In fluid mechanics, for example, this is the velocity variation. The horizontal axis is the velocity. The vertical axis is the distance from the wall. This red line is called a boundary layer velocity profile. So velocity is zero velocity, increases some more, and so forth. The entire boundary layer thickness is of the order of delta. So the velocity goes from 0 to some edge velocity capital V over a short distance delta. Therefore, if somebody asks you what is the slope anywhere in this curve, I don't know, a rough order of magnitude of the slope, you would say it's going to be of order of how it goes from 0 to V over a distance 0 to delta. So V over delta is what it is. So in the absence of any new information, quantitative or analytical estimate, all he could do is do a crude estimate like this for an order of magnitude. So this is what Prandtl did. He did know that this delta, which is the boundary layer thickness, is very, very small compared to the length of the flat plate or the length of the chord of an airfoil. So if you take a conservation of mass, which has got two terms, du dx and dv dl. So x is in the direction of the flow, so the length scale is L. U is the extreme velocity, so it's proportional to v infinity or the edge velocity v. So this slope is of the order of v over L. The letter O means of the order of. This is the V is the free stream velocity and L is the length of a flat plate or length of the chord, depending on whether we are talking about a flow over a flat plate or flow over an airfoil. So this is just one term in the conservation of mass. Now we have two terms balancing each other. So this we estimated it as V over L. So here, we don't know the magnitude of the vertical component of velocity because not enough information is known, so we are going to leave it that way. But we do know that the y is of order of delta. Therefore, we say this term is of this order, this term is of this order. Of course, they have to be the same order, equal and opposite in sign, so that they add up to 0. So you can estimate now this little v has to be capital V times delta over L. So little v should be of the order of v times delta over L, because all I have done is taking this delta to the other side. Then if you bring the v, capital V, to the denominator, the vertical component of velocity as a fraction of the free stream velocity or the reference velocity is of the order of boundary layer thickness divided by the flat plate length or the chord length of the airfoil. We mentioned this is of the order of millimeter or 10 millimeter, something very small. The length is of order meter. So this ratio is 1,000, 1 over 1,000 or smaller. Therefore, the vertical component of velocity in the boundary layer is very, very small compared to the horizontal component of velocity, especially in the outer flow, where the velocity is like the free stream velocity. Very small velocities in the direction transverse, or in the normal direction, perpendicular direction in the viscous layer. So we have now gotten something out of conservation of mass without doing a calculation or lifting up a calculator or going to the computer. So Prandtl said, I'm going to do the same thing for the other terms in my U momentum equation. So wherever I have a U, I'll stick in a reference velocity capital V. Reference velocity capital V. Wherever I have an X, I'll put an L. V is of the order of V delta L from the previous slide. U is of order V. Y is of order delta. So this delta and this delta will cancel. So this becomes order of V squared over L. So this is of order of V squared over L. V squared over L. V and L are pretty big numbers, therefore we can't really neglect this term or this term. How about the pressure gradient? We know from Bernoulli equation, pressure energy plus kinetic energy are of the same order. So P and rho times velocity squared are of the same order. Rho and rho cancels, so we get a velocity squared in the outer edge of the boundary layer divided by X is of order L. Again, we get order of V squared over L. So all the terms on the left-hand side are of the same order, therefore they cannot be neglected. Our only saving grace is viscosity is a very, very small number. So Prandtl was hoping that some of these terms will go away. If all other terms go away, we get an inviscid flow, which is not meaningful. If we keep both the terms, we get Navier-Stokes equations, which is not meaningful. Therefore, we need to see which one of these two are relatively more important and keep the term multiplied by a very small number, you keep that particular term. So that's what Prandtl rationalized. So on the right-hand side, U is of order of velocity. You have a derivative of x with respect to derivative of x. Therefore, you'll pick up an L times L, so V over L squared. This is a large number multiplied by a very small quantity. But if you look in here, this is capital V, this is delta squared, Y is of order of delta. Between these two terms, this is the most dominant term. Therefore, he said, I'm going to neglect this number, this quantity times a very small number, in preference to a very small number times even larger number. So he kept this term, he neglected this term. It's like when you're in pocket, you have a $1 bill and a 10-cent coin, you are more willing to give up your 10-cent coin and keep the $1 bill. On the other hand, if you had a 2-cent coin, a 10-cent dime and a nickel, you're likely to keep both of them. So when numbers are of the same order, you keep them. When two numbers are of different orders, you throw away a smaller number relative to the larger number, particularly when this whole term is going to be multiplied by a smaller number. So this is what Prandtl did. So the Prandtl's U momentum equation looked like this. Notice it's got now the second order boundary condition only in the Y direction. That means you need to know what's happening at the wall, what's happening at the edge of the boundary layer. You don't need to know what's happening far upstream. You don't need to know what's happening far downstream. So somewhat simplified formulation has resulted. If you're solving the flow field in the nose of an aerofoil, you don't need to know what's going on in the trailing edge because I don't have any second derivatives in respect to x at all. Then he said if the left sides are all of V squared over L, if the right side is of order of kinematic viscosity times the free stream velocity over delta squared. This must balance this one. So this must balance each other. So he took the delta to one side, divided by L squared, delta squared over L squared. Then he found it was of order of kinematic viscosity times free stream velocity times L. So rho VL over molecular viscosity is called Reynolds number. Therefore, this is 1 over Reynolds number. Therefore, the boundary layer thickness as a fraction of the aerofoil core is simply 1 over square root of Reynolds number. So he got a very powerful result for the thickness of the boundary layer. We will do the V momentum equation and stop this particular video. So the shear layer thickness is very thin. Reynolds number is of the order of 1,000,000. Square root of Reynolds number is of order 1,000. Therefore, the shear layer thickness, boundary layer thickness as a fraction of the core is 1 over 1,000. This is the case when mu is a constant molecular viscosity. In turbulent flow, it could be somewhat thicker, but not dramatically thicker. For the time being, we are dealing only with laminar boundary layers. Therefore, sometimes boundary layers are called shear wall-bounded shear flows because there's a lot of shear stress there. The wake, it would be called a free shear flow because it's not bounded by a wall. But they are all laminar flows because of molecular diffusion. Later on, we will talk about turbulent flow due to the eddy mixing the flow. So how about the V momentum equation? Again, we can go term by term by term. U dV dx will be U is of order of V. V is of order of V delta over L. X is in the denominator, therefore it's 1 over L. So what order of V squared over L times delta. Now delta over L is 1 over square root of Reynolds number from the previous slide. Therefore, this term is of order something times 1 over square root of Reynolds number. So Reynolds number is like 1,000,000. So 1 over square root of Reynolds number is 1 over 1,000. So this term is relatively small. So he did this term by term by term. Then he found all these terms were very, very small. Therefore, it also follows that 1 over rho dP dy, even though it says got a y in here, it's got a delta in here. If all the other terms become small, this term also better be small. So he did a careful analysis of term by term. Then he came up with this is simplified equation across the boundary layer. That means the pressure does not change across the boundary layer. If you know the pressure at the edge of the boundary layer in the outer region, then you can assume it's the same pressure all the way across the boundary layer. So the V momentum equation is very, very simple. So we would first solve the outer flow first, get the pressure field. Then once you know the pressure at the edge of the boundary layer, all the way towards the wall, you can keep the same pressure. So this is the summary of the equations that we have developed. Conservation of mass, conservation of U momentum, conservation of V momentum, order of estimate for the vertical component of velocity, normal to the boundary layer wall. Here is the boundary layer thickness as a fraction of aerofoil. So Prandtl did all of these with just a pencil and paper, without a calculator, without a computer, without going to any math class, any physics class, just a piece of paper, a pen, and maybe a glass of beer by his side. He got all these relationships. So this is called the Prandtl's boundary layer equations. So we are going to delve into this a little bit more in our next series.